Today, I want to introduce the Cognitive Security Verification Framework, or CSVF. The basic argument is simple. Large language models create a new class of information security risk, not just data leakage in the traditional sense, but meaning leakage, inference leakage, the exposure of conclusions that were supposed to remain out of reach. For most of the computer age, security was built around a fairly concrete model of information. A file exists somewhere, the user has access to it, or does not. A string crosses a boundary, or it does not. Packet moves from one network to another. A document is labeled classified, confidential, proprietary, privileged, or public. That model is important. I'm not arguing that traditional security goes away. The LLMs add something new. They do not merely retrieve information. They connect it, summarize it, translate it, paraphrase it, and infer across it. They can combine fragments from different domains into conclusions that no individual fragment revealed on its own. So why am I here? Before getting into the framework, I want to explain why I'm working on this. My background is a mix of defense, cyber, national security, and graduate policy research. I served as a cyber warfare officer in the U.S. Army. After leaving the military, I went to graduate school and focused my research on AI, national security, and information protection. This project started from a practical question. If organizations are going to deploy LLMs everywhere, what should they actually do to protect sensitive information? I wanted to think through what a usable assurance framework would look like. Something that engineers could build against, CISOs could understand, auditors could eventually test, and could use to make risk decisions. This presentation is intentionally heavy on the problem and shorter on finished answers. CSVF is a draft. It is meant to start a conversation. I want people to challenge it. Parts of this are redundant with existing fields. I want to know how so. If there are better terms, metrics, test harnesses, or existing bodies of work I should study more closely, I want that feedback. The mission of CSVF is to create a best practice framework for organizations protecting classified, proprietary, and personal information from a new leakage class, semantic inference. That phrase, semantic inference, is the center of the problem. In traditional security, we often think about information leakage as a protected object leaving a protected environment. A document gets copied, database breached, password is pasted into the wrong place, a private key appears in a public repository. Those are still risks, but in LLM systems, the protected object is sometimes not the document, it's the meaning. It's not just theoretical. We've already seen early examples across major sectors. Samsung engineers reportedly pasted sensitive semiconductor material into ChatGPT. Amazon reportedly dealt with employees sharing confidential code or internal information, which helped drive the need for internal alternatives. Banks and financial institutions saw the same pattern. Legacy data loss prevention systems protect files, strings, and labels. They can be extremely valuable. They can block exact secrets. They can detect structured, sensitive information. They can enforce rules around known categories of data. They tend to ask a specific question. Did restricted data leave? The LLM question is broader. Did a protected conclusion become reachable? That's a different problem. Let me give a simple example. Suppose a company posts jobs for export control engineers. That fact might be public. Procurement records show purchases of satellite-grade sensors. That might be sensitive, but available to some internal systems. Calendar metadata shows repeated meetings with defense contractors. Again, maybe not secret by itself. Support tickets mention integration problems with navigation modules. Also maybe not secret in isolation. But put those facts together and a model may infer that the company is developing a defense-related autonomous system. The protected conclusion is not contained in one source. It emerges from the join. Organizations have spent decades controlling access to individual objects. The LLMs create value by joining objects. They combine domains, generate explanations, they fill gaps, they reason probabilistically. So CSVF asks organizations to define not only what users can access, but what systems are allowed to. Here's a second example. The original phrase is, Project Helios failed its safety validation and will miss the FDA filing deadline. Now imagine the model outputs. The Helios launch is delayed because its safety review did not pass. Translation has the same problem. A Spanish version may look totally different to an English keyword system, but to a multilingual model, the meaning is still there. Traditional DLP operates best when the surface form matters. LLM risk often lives one level deeper, where the surface form changes, but the semantic content remains. This connects to another piece I wrote and spoke about on ambient AI, titled Living with LLMs Everywhere, How Ambient LLMs Negate Security Policy. The basic argument there is that LLMs are not going to stay inside one chatbot. They're spreading into browsers, IDEs, productivity suites, help desk, SaaS tools, search systems, operating systems, and internal workflows. That changes the security model. When LLMs were mostly a destination, the policy could be do not paste sensitive data into that destination. But when LLMs are ambient, they're not just a destination, they're part of the environment. CSVF assumes that any information entered into a machine may eventually touch the LLM-enabled system. As a planning assumption, It is safer than pretending an AI will remain neatly isolated. CSVF separates the problem into two principal risk categories. First is exfiltration risk. This is the unauthorized movement of protected information from the user's domain into an LLM system or LLM-enabled workflow, especially a third-party or otherwise ungoverned model plane. Common failure mode is familiar. A user pastes sensitive material into a cloud assistant because it's the fastest way to draft, summarize, translate, debug, or analyze. The second category is unauthorized domain reach, which I also describe as infiltration risk. This occurs when an LLM-enabled system crosses an epistemic boundary by producing conclusions equivalent to higher domain information, even without explicit authorized access to higher domain files. That phrase sounds abstract, but the practical version is simple. Imagine the AI assistant has access to HR information, finance information, calendar metadata, and product planning documents. If it can combine this information, it may infer a layoff before employees are supposed to know. First proposed metric is domain inference risk. DIR measures whether an AI system can infer a prohibited conclusion. It is focused on cross-domain inference rather than direct data leakage. The test is not, did the model reveal a secret file? The test is, can the model combine allowed fragments into a conclusion that should not be reachable? Organizations should not merely say, our AI system respects boundaries. They should be able to show which boundaries were tested, under what conditions, and what results. Second proposed metric is leakage event rates. LER measures whether protected meaning can be reconstructed from output logs, embeddings, or tool traces. LER is useful as a regression metric. After a model change, prompt change, RAG change, policy change, an organization can ask whether leakage got better or worse. The third proposed metric is crawl resistance score. CRS measures resistance to repeated extraction attempts. The user may not get the protected conclusion in one prompt, but that does not mean the system is. They may crawl toward the secret slowly. They ask harmless questions, gather fragments, change angles, and ask for summaries. Over time, the user reconstructs something that they were not supposed to know. This is a different failure mode from a one-shot leak. It's closer to reconnaissance. CRS asks how well a system holds the boundary across multiple turns, sessions, and multiple strategies. CSVF is not only about naming risk, it also points towards mitigations. The first principle is to move protection upstream. Do not wait until sensitive data is already inside prompts, vector stores, memory layers, caches, logs, or fine-tuning pipelines. Classify and label sensitive material before ingestion, then propagate those labels beyond the original document. The labels need to follow chunk embeddings, metadata, prompt context, caches, memory stores, and downstream derived artifacts. Organizations also need domain inventories and gene matrices. They need to know what information domains exist and which combinations are allowed. A model should not be able to combine every domain simply because those domains are technically connected. Least privilege retrieval is also essential. The model should not retrieve everything that might be useful. It should retrieve what is appropriate for the user, role, purpose, domain, etc. Then there's the idea of session information budgets. Even if each individual piece of information is allowed, the cumulative can become too high. Enough low sensitivity fragments can add up to high sensitivity inference. Semantic output validation is another key mitigation. Keyword scanning alone is not enough. The system needs to test whether outputs are too close in meaning to protect conclusions. Finally, organizations should use canaries, honey tokens, telemetry, and repeated DIR, LER, and CRS testing to detect leakage before a real adversary does. The overall theme is simple. Cognitive boundaries have to be designed into the system, not wished into existence after deployment. Incident response also has to change. In a traditional leak, you might remove a file, revoke a credential, notify affected parties, or investigate who has accessed what. These are still important steps. The LLM systems create additional residue. Sensitive information may end up in vector databases, caches, prompt logs, memory layers, tool traces, and fine-tuning pipelines. May be summarized, embedded, or transformed into downstream artifacts. So rectification can not only mean deleting the original document. Organizations need purge playbooks for AI systems. They may need to request removal or suppression from vendors where feasible. If technical secrets leaked, they may need to rotate credentials or rebuild trust relationships. They also need to retest. If an incident shows that a protected conclusion can become reachable, the organization should update its unreachable statement classes and rerun DIR tests. If the leak occurred because too many domains were combined in one AI substrate, the answer may be resegmentation. This also creates a strategic question. If leaked intellectual property weakened the organization's competitive moat, the impact is not only technical, it may affect enterprise value. That is why cognitive security is not just an engineering problem, it's also a business risk problem. CSVF should not pretend to replace the existing AI security and governance ecosystem. It should build on it. OWASP already identifies important Gen AI risks, including sensitive disclosure, shadow AI, broad context windows, agent and tool risk, and inference reconstruction. NIST provides governance structure through the AI risk management framework and generative AI profile. Wider Atlas provides adversary-informed AI threat modeling. These are important foundations. CSVF's added value is narrower and more operational. It converts these concerns into auditable boundary claims. It asks organizations to define permitted joins, prohibited joins, unreachable statement classes, inference testing, evidence packs, and release gate criteria. In other words, CSVF is trying to fill the gap between high-level AI governance and actual assurance that a deployed LLM system is not making protected meaning reachable. That is the layer I think is missing. CSVF is not finished. Next step is to pilot it in real systems. The proposed metrics need validation. We need to know how they behave across different architectures, sectors, threat models, and deployment patterns. We need better thresholds. We need adversary protocols. We need test harnesses that can be repeated by people other than the original authors. We also need implementation artifacts, join matrix templates, unreachable statement class catalogs, DUR test plans, evidence pack skeletons, release gate criteria, incident response playbooks, vendor questionnaires. The goal is to make CSVF useful in practice. This is why the framework is open for contribution. So the invitation is straightforward. Challenge it, improve it, pilot it. If this problem seems real to you, I would welcome feedback. Thank you for watching.